Have you ever watched a firecracker explode instantly while rusting takes weeks to be noticed? Why do some reactions happen in a blink and others take days, months, or even years? That difference, the speed of a chemical transformation, is captured in a concept we call the rate of a chemical reaction. In simple terms, the rate tells us how quickly the concentration of a reactant or a product changes over time. It's defined as the change in concentration per unit time. The unit for this is usually mole per liter per second, that is, mol L superscript 1 S superscript 1. Let's take a classic reaction. Hydrogen gas reacts with iodine gas to form hydrogen iodide. That's written as H2 gas plus I2 gas gives to high gas. The rate could be measured by how quickly the concentration of high increases or how quickly H and I decrease. As you can see in the graph, reactant concentrations drop while product concentrations rise. This simple plot hides a lot of powerful chemistry. Let's break it down further.
Not all reactions proceed at the same speed throughout. So we define two important types of rate: average rate and instantaneous rate. The average rate is like looking at the total change over a time interval. It's calculated as the change in concentration over time, written as delta R by delta T. But sometimes we want to know what's happening right at a specific moment. That's where the instantaneous rate comes in. It's found by drawing a tangent to the concentration time graph and measuring its slope at that point. So while the average rate gives us the big picture, the instantaneous rate zooms in, perfect for tracking fast changes or peak reactivity in a reaction. If you refer to the graph on screen, the second line shows the average rate over a time period, and the tangent line shows the instantaneous rate at a specific time.
Now let's talk formulas, the heart of chemical kinetics. For a general reaction, R plus BB gives CC plus DD. We express the rate as rate equals K into concentration of A to the power M times concentration of B to the power N. Here, K is the rate constant and M and N are the reaction orders with respect to A and B. But keep in mind, these exponents are not necessarily equal to the stoichiometric coefficients. They're determined experimentally. The rate constant K varies with temperature and is different for each reaction. Its units depend on the overall order of the reaction. For instance, if it's a first-order reaction, K has units of per second. For a second-order reaction, it's liter per mole per second. We'll explore these rate laws more deeply when we study reaction order, but for now, just remember this equation captures how concentration affects reaction speed. Now, why does the rate of a reaction change under different conditions? Several factors control how fast a chemical reaction happens. First, concentration. More reactant particles mean more collisions, which leads to faster reactions. Next, temperature. As temperature increases, particles move faster and collide more energetically. That's why reactions usually speed up when heated. There's also the role of a catalyst, a substance that lowers the activation energy by offering an alternate reaction pathway. The reaction speeds up, but the catalyst itself remains unchanged. Other factors include surface area for solid reactants and pressure for gaseous systems. More surface or higher pressure means more effective collisions per second. Refer to the energy profile diagram with and without catalyst. Notice how the catalyst lowers the energy barrier. That's the secret to faster reactions. Let's now go from theory to the lab. How do we measure a reaction's rate? We track a measurable property that changes over time. It could be the volume of a gas, the change in pressure, mass, or even the color or pH. Here's a familiar experiment. Zinc reacts with dilute hydrochloric acid to release hydrogen gas. We can measure the volume of gas evolve over time using a gas syringe, giving us the rate of hydrogen formation. Other techniques include titration for acid-base reactions or colorimetry when color changes. Even conductivity and pH meters are used in ionic reactions. The idea is simple: track how something measurable changes over time, and you've captured the rate. Let's solve a numerical example to bring this all together. Suppose the concentration of a reactant drops from 0.10 mole per liter to 0.04 mole per liter in 3 minutes. What's the average rate of the reaction? Step 1. Apply the formula average rate equals initial minus final concentration divided by time. That's 0.10 minus 0.04, giving 0.06 mole per liter divided by 180 seconds. The result is 0.000333 mole per liter per second, or 3.33 times 10 to the power minus 4 moles L superscript 1 S superscript 1. That's how we use real data to calculate rate. It's that straightforward. So, to sum up, the rate of a chemical reaction tells us how fast reactants turn into products. We've seen how it can be average or instantaneous, and how it's linked to concentration, temperature, pressure, and catalysts. We learned the rate law formula. Rate equals K into concentration terms, and how the rate constant K carries key information about the reaction and its order. From lab-based measurements like gas volume and pH to real-life reactions like cooking, rusting, or even digestion, chemical kinetics helps us quantify and control the pace of change. I hope this session helped you appreciate how chemistry isn't just about what changes. It's also about how fast. Catch you in the next class, where we continue to unravel the fascinating world of chemical transformations.